In this video, we're going to talk about the equations of circles, what those equations look like, some various forms, as well as a little bit of graphing in there as well. So while circles are not functions mathematically, they would fail the vertical line test. Being able to graph them and work with their equations is pretty important in a lot of cases, especially if we get to some trigonometry. The standard equation of a circle with center at h comma k and a radius of r is x minus h squared plus y minus k squared equals r squared. Note that the formula is defined with subtractions, a minus h, but the x-coordinate of the center is just h. And it says y minus k, but the y-coordinate of the center is just k, and that the radius has been squared on the other side of the equation. Now, within this, we do have a couple of special cases that we want to be able to work with. One is when the center is at the origin. A lot of our circles will work with that. So if the center is at the origin, that means our center point has coordinates 0, 0, so that our equation becomes simply x squared plus y squared equals r squared. And you'll notice there that that looks awfully similar to the Pythagorean theorem, a squared plus b squared equals c squared. And the reason being is that the radius is a distance, and the distance formula comes from the Pythagorean theorem as well. So there's a lot of relation between equations of circles, the distance formula, and the Pythagorean theorem. The second special case of the general case is still going to have our center at the origin, but we're also going to have a radius of 1. So I would just take the previous example that I had, x squared plus y squared equals r squared, and it becomes x squared plus y squared equals 1. That circle, that very specific circle, centered at the origin with a radius of 1, has a special name, and it is called the unit circle. And you will deal with the unit circle a lot when you're studying trigonometry. We'll graph that a lot. We'll use a lot of the points in its equation. So that's a nice special case. For the most part, however, we are going to concern ourselves with the general case, x minus h squared plus y minus k squared equals r squared. What we're going to do now is just work through a couple of examples of writing an equation. So if we're going to take that, and you had information that the equation of a circle has a center at 5, negative 7, with a radius of 13. I would use my formula, x minus h squared plus y minus k squared equals r squared, and just substitute the appropriate values in. So it would be x minus 5 plus, now it's going to be y plus 7, because my y-coordinate of the center is negative 7. Y minus negative 7 is the same as y plus 7 squared equals r squared. So that'll be 13 squared, which is 169. So there's the standard form of the equation of a circle centered at 5, negative 7, with a radius of 13. Now, let's say we don't have all that same information. Find the equation of the circle that has a center at negative 2, 3, and contains the point 4, 5. I cannot write the equation of this directly, so I am going to use the distance formula first to find the radius. That the distance between the 2 points, the distance between the center of the circle and any point on the circle, is going to be the radius. So I will have this square root of the difference of the x-coordinates squared plus the difference of the y-coordinates squared. That is going to give me the square root of negative 6 squared plus negative 2 squared. So the square root of 36 plus 4. That gives me the square root of 40. I know that can be simplified to 2 root 10. I could get a decimal approximation. I could do a lot of things. But in this case, we're going to leave this square root of 40 as is. And the reason being is when I get into my circle formula, now that I have my center and I have my radius, what I will notice, now my center, let's see, my center is going to be x plus 2 squared. Let's look at this whole page here. My center has an x coordinate of negative 2, so it's x plus 2 squared, plus y minus 3 squared equals r squared. Well, my r is the square root of 40. I have to square it. The square root of 40 squared is simply 40. Had I done extra work on this square root of 40 to simplify it, I would have had to undo that work when I square it. And then had I turned it into a decimal, I probably would have had to round that decimal, truncate it, do something, and then I would have squared that decimal, and I would not have gotten my 40 back exactly. I either would have gotten 39 point something if I had rounded down, or truncated. Maybe if I rounded up, I would have ended up with like 40 point something. But instead of getting that nice, neat integer 40, that exact value, I would have ended up with some other value. All right. So just a couple of examples about how to use and how to write the equation of a circle in standard form. Now, there is an alternate form of the equation of a circle. And that alternate form is simply going to be, if you take your standard form, if you expand the binomials and move the constants to the right, you will get the alternate form. In this particular case, I have x plus 2 squared plus y minus 3 squared equals 40. That tells me, that's the last equation that we have. So that's that circle centered at negative 2 comma 3 with a radius of the square root of 40. But if I took and expanded out all these binomials, and I went with x squared plus 4x plus 4 plus y squared minus 6y plus 9 equals 40, went x squared plus y squared plus 4x minus 6y equals, now 9 plus 4 on the left is 13, so I'm going to subtract 13 from both sides. I get 27. This form is that alternate form. Now, it doesn't give you any information about the circle. That equation I have in the yellow box, it doesn't tell me the center. It doesn't tell me the radius. It doesn't tell me about the location or size. But we do have other forms of equations that do that. It's similar to standard form of a linear equation, ax plus by equals c. I'll write that down there. Ax plus by equals c. That's standard linear form, as opposed to something like slope-intercept form. They're both forms of linear equations. It just so happens that slope-intercept form gives us information about the line. Standard form doesn't give us anything. It's just one of those forms that just doesn't give us any information, but it does exist. And we have this same idea here for the alternate form for the equation of a circle. And converting from standard form to the alternate form is pretty easy. Just expand the binomials, move the constants to the right, you're just reorganizing some terms. That's pretty easy. But if we want to work the other direction, we have to be able to complete the square. So if I have this equation, x squared plus y squared plus 8x plus minus 10y plus 37 equals 0. Now in this particular case, the 37 is on the same side. And I want to go back to the standard form so that I can identify my center. Wrong item there. My center and my radius. I want to have my equation in that standard form. So how do I take the equation that I have, my x squared plus y squared plus 8x minus 10y plus 37 equals 0, and how do I get back to my standard form? Well, the only way to do it is to use our old friend from our quadratics, complete the square. And in actuality, we're going to do it twice. Once for our terms involving x, once for our terms involving y. So I'm going to take a moment here, and I'm going to collect my x's together. I'm going to leave a space for my completing. Collect my y's together, leave a space for completing, and move the constant to the other side. So now I have x squared plus 8x, leave a gap, plus y squared minus 10y, leave a gap, equals negative 37. And the completing the square process will be to fill those values in so that each variable has a perfect trinomial square. For x squared plus 8x, I'm going to add 16. For y squared minus 10y, I'm going to add 25. But that means on the right side, I'm going to have negative 37 plus 16 and plus 25 to make sure my equation stays balanced. When I do that, these three terms are a perfect trinomial square, giving me x plus 4 squared. The next set of terms is another perfect trinomial square, giving me y minus 5 squared, equals, now 16 plus 25 is 41. 41 with negative 37 gives me 4. Now my equation, I've gone from the alternate form back to my standard form, so that I can see that my center is at negative 4 comma 5, and I have a radius. Now remember, in the equation, the radius has been squared, so my radius of this circle is 2. So we've covered here the standard form of equation, how to write equations in those sorts of forms, and how to convert the alternate form back to the standard form by completing the square. Here's another example for you, just because this can come up sometimes. And what we need to remember in this particular case, find the center and radius of the circle whose equation is 3x squared plus 3y minus 12x plus 18y equals 9, is that we can't complete the square unless our leading coefficient is 1. So what we're going to do is start by taking the equation 3x squared plus 3y squared minus 12x plus 18y equals 9. And I'm going to start by dividing both sides by 3. So I have x squared plus y squared minus 4x plus 6y equals 3. Now I can move into the completing the square process. I would suggest to you that you pause the video, try to do it yourself, come back and watch the worked out solution. All right, if you're back, I would start by arranging my terms. Creating my perfect trinomial squares by taking half of the linear coefficient and squaring it. Making sure to add those values to both sides. Rewriting my perfect trinomial square as a binomial squared. Simplifying the other side. And so now I can say that my center is at 2, negative 3, and I have a radius of the square root of 13. Remember that the number on the right side is the square of the radius. So when I actually state the radius, I need to take the square root. I hope this gives you a good introduction to the equations of circles, and that the rest of your work from here goes well. Thank you.